Hello guys, welcome to another tutorial. In this tutorial we're going to talk about GLSL shaders, and we are going to work with jit.gl.shader. Let's call this GLSL, which is the name of my render context. So what's a shader? Shader is a program that works on the GPU. It's a lot like gglpix. gglpix is actually a fragment shader, while an actual GLSL shader is composed by a vertex shader and a fragment shader. So we are going to build both of these inside our GLSL shader. So first of all, let's open this. We are going to build a light shader. So a shader that simulates the light for our shape. So let's create jit.gl grid shape. Let's call this GLSL. Scale 0.5, dim 400 by 400, pretty big. And let's give it, yes, the shader attribute. So the vertices and the color of this shape are going to be modified by this shader, which has name light shader. Right? So let's open GLSL Shading. This is a white canvas. This is actually a txt file, but we need to have a JXS file, which is an XML based file in which shaders are written here in the jit.gl shader environment. So first of all, I don't really like to work with the default editor here. So I prefer to use Sublime, which is a program you can download. And Sublime is a code editor. It works really well. It's pretty great. So first of all, we have to name our JIT shader. We have to give this a name. I'm going to call this light shader. We can choose the syntax here for Sublime. Since GLSL is pretty similar to C, I'm choosing the C syntax. And you can add the description for this shader. I'm going simply to write light shader. This is optional. And we are going to close this with a slash. Then we need to add some parameters to our shader. We have to give a param name. We need the shininess parameter. And we need to define its type, which is float. And we have to set a default value like 16. This shader is mostly taken from the Orange book, which is the official GLSL book. So this is greatly taken from this book, but with some extra explanation. We need another parameter, which is text 0, type int, default is 0. This is the index of our texture that we are going to use. Then we have to define the language name, because we can write shaders in some languages different from GLSL, but we are analyzing the GLSL language. Version 1.0, which is a pretty old version. Then we need to bind those parameters to our programs, which is assign the parameters to to one of the two programs, the vertex program and the fragment program. So we need to assign the shininess to the vertex program, and we need to assign the text 0 to the fragment program. Yes. Then we need to write our actual vertex shader. So program name is VP, which stands for vertex program, and type vertex. And we can start. We need to declare this C data, and we can start writing our vertex program. So first of all, we need to define our varying variables, which are variables that are passed from the vertex program to the fragment program. So we define them in the vertex shader, and then they get interpolated and passed to the fragment shader. So our first varying variable is the light intensity. Now our only varying variable, which is the computed value for the light on every vertex of our shape. Let's see. Why is this a back 4? Because it's a color value, so it's formed by 4 floating numbers. This is a lot like writing back with 0 values here in the jit.gl environment. So we defined our varying variable, and then we need to build our actual main function, which is the body of our vertex program. So first of all, we need to define a vec3 value, which is the coordinates of our vertex in I coordinates. Yes, these are the I coordinates of our vertices. What I mean with I coordinates, let's see. Those are this is our shape, and when it's passed in the vertex shader, it's actually in model coordinates. When the vertices are passed to the vertex shader, they are passed in model coordinates, where the center of the system is the center of the shape. We need to transform those coordinates in I coordinates, where the center is the camera. 0, 0, 0 is the camera position, and every coordinate from the shape gets transformed to match those coordinates. I hope this is clear enough. So we need to get the I coordinates. We need to multiply the GL model view matrix by the GL vertex. So what is this? So this is a matrix and this is a vector. And when you multiply a matrix by a vector, you're actually transforming that vector. And this model view matrix transforms this vector in a way that now it is in I coordinates. Right? We need it in I coordinates because the lighting calculation is done in I coordinates. Right? Then we need the I coordinates components of the normal to that vertex. So we need to normalize the result of the GL normal matrix multiplied by the GL normal. We don't need to get only the first three values with this vec3 constructor, because the GL normal matrix is a mat3 and the GL normal has only 3 components, while the GL vertex has 4 components. So we don't need the vec3 constructor, but we need to normalize the normal components, right? Now we need light vec. What's the light vec? It's a vector that goes from our shape to the light. So is this vector here. How we calculate this vector? Yeah, first of all, we have to normalize the result. We have just to get the light source 0. This is a built-in uniform we find inside the GLSL. This is actually the light position that we can set from our jit.gl render. This is this. We can modify this light position attribute, and we are modifying this jit.gl light source 0 position value, and we have to get, we can swizzle the x, y, z, zeta values like in jit.gl pics. We can swizzle them with the point and the name of the components we want to swizzle. And we have to subtract from this our A chord vertex position. So this way we are creating this vector, right? Because this is the head, this is the tail, and you know that we subtract the tail from the head, we are getting the components of this vector, and this is normalized. So it's just a direction vector now. Then we need the reflect back, and to get the reflect back, we have to use the reflect built-in function inside the GLSL, which takes the opposite. It takes this vector, the incident vector on the surface from the light source. So we have to negate this vector to change, to inverse its direction. And then we need the I chord norm. So this is the reflection vector between the normal to the surface, which we can say is this, and the light, sorry, let's say it's this is, let's change this. Yes, let's say that this is our light vector, incident vector. This is the normal to the surface, and so this is our reflect vector, something like that. All right. So we need this reflect vector. And this is actually a normalized vector because we are using both normalized vectors. Then we need the view back, which is the vector that goes from the viewer. So let's say we are here, we are the viewers, pretty creepy. Yeah. And let's say the view vector is the vector that goes from the vertex position to the viewer position, which is the camera position, which is 0, 0, 0. So that's the view vector. And we need to get the view vector, we need to subtract the 0, 0, 0 position. So we need to subtract the I-chord vertex to the 0, 0, 0 position, but this is just equal to negate the I-chord vertex vector. Alright, so we can now calculate the diffuse component of our light, which is the light that gets scattered by the surface. To do this, we have first of all to do the dot product between the light back and the normal, which is this. You know, the dot product between two normalized vectors is just the cosine of the angle between them. It's just this, the cosine of this angle. So we need to get the max between the cosine and the 0, because if we have a normal here, it's not under the light because it's covered by the surface. This point of our shape doesn't get lightened. So we have to perform this calculation in a way that if the angle is greater than 90 degrees, the cosine gets lesser than 0. But we are using the max function to clump it between 1 and 0. That's because we don't want this point of the surface to get lightened. Alright, let's proceed. We now can calculate the specular component. Let's define it like 0.0, and let's say that if diffuse is greater than 0.0, then the specular component is equal to the max between the dot product of the reflect back and the view vector. So this vector and this vector, the dot product of these two must be greater than 0, because otherwise we are just getting 0. And this is for the same reason of the diffuse calculation. We don't want the specular highlights, which are something like that. We want them to be we want the highlights to be greater when the reflect vector and the view vector are nearly the same. So when the view vector and the reflect vector are nearly the same, we get the most highlights. Otherwise we get less highlights. So we use the same dot product we used before. I hope this is clear enough. For every question, don't hesitate, ask me. We must now elevate, get the power of the spec for our shininess value, which is a parameter, so it's accessible in our max environment. So if we create a message here called shininess, we can access the shininess value inside our GLSL shader, a lot like a parameter for the jit.gl.pix object. Right, now we can finally compute our light intensity, which is equal to GL light source 0. The zeros is because we could have a lot of lights, and this is like an array of lights. Because we have just one light for the moment, we're taking the 0 number in this array, which is the first light. and we get the diffuse value, which is this light diffuse. Is the same value we can choose by this render attribute. We multiply it by our diffuse value, and we sum to this another light source, the light source specular highlights. We multiply this by our spec value. Then we have to do what every good vertex shader does, which is pass the vertex position to the fragment shader. And to do this, we use the built-in function fTransform. This performs a matrix transformation to the vertex to transform it in window coordinates. And then we have to also pass the texture coordinates, because we're going to use a texture. To do this, we need to access our texture matrix 0 always, because it is an array of textures. And we have to multiply this. So we have to multiply the multi-text chord 0, which adjusts the coordinates of our texture, by this matrix that retains all the transformations applied to that texture. So our vertex shader is complete. We have to close these. We have to close also here with the program. And we now have to write our fragment shader, which will be a lot shorter. We have to name this type equal fragment, and let's write c data, and let's write our program. So we need to declare here our varying variable, the same which we declared in our vertex shader. And we also need to declare a uniform, which is a parameter that we can access from the outside of the shader program. Also have to declare a uniform here for the vertex, because the shininess is actually a uniform. Everything we declare as a parameter, we have to declare as a uniform here in order to access it in the shader program. So we need to declare our texture as a sampler 2D, which is the texture format here in the shader. We have to write our main function. We have to create vec4, which is the color of our texture pixels that are actually called texels. And this is accessed by the texture to the operator, which takes our texture and our GL text chord that we are passing from the vertex shader. This is like a varying variable, but we do not have to declare it here because it's built in. So we are accessing our texture with a GL text chord. This is like using a sample inside our jit.gl peaks with the norm coordinates. All right. So now we have to assign this vertex color to the final output of our fragment shader. So we have to assign the texture color multiplied by the light intensity, and we have to add to this the ambient light that we also can choose from our jit.gl render. Right, this is it. We have to close this, and we have to close the program. All right, we have to close the language too, and we finally have to close the jit shader. All right, that's our shader. I hope it works. Let's see. Let's create a texture, jit.gl texture, GLSL, name text 0. It doesn't need to be equal to our text name here, but for clarity, we can do this. We also have to check that the rectangle attribute is set to 0, because otherwise we should use the rect texture to the rect operator and sampler to the rect, because without the rect word we are using normalized texture coordinate, and with the rect we are simply using unnormalized integer texture coordinates. So let's read our texture, fire text, and let's see what we got here. Right. Let's see. Of course, it's not working. Of course, let me see why. Oh, of course. First of all, we didn't give the texture attribute to our shape, and then that's because we don't have any file here in our shader. We have to give it the file name, like shader.jxs. It says that it has an error. We lack an equal here. Okay, now it should work. Let's load our texture. All right. So this is it. This is our textured and lighted shape with our custom material, we can say, our custom shader. You see the highlights. If we reduce the shininess value, which is the power, is the power value here, we get more highlights. We can move our light with the light position from here. See, and yes, we can change also the diffuse color of the light, and we can also change the specular component of the light. So it's like we have red specular highlights. So yes, guys, this is it. I hope you found this useful. For everything, feel free to contact me, and let's see you in the next tutorial. Thanks for watching, guys. Bye.